Okay, hey guys, I think this thing is recording now. So we're in the beginning of chapter 4. So we're going to start chapter 4. This will be the last chapter we're going to cover before we take our first test. And this one's going to have some new stuff in it at the end of the chapter, not so much at the beginning. But the plan is that I just got a text, but the plan will be your labs are due Monday, Tuesday, the hydrate lab. The quiz, chapter 3, is due Wednesday, Thursday, and we're going to do it. The plan will be we'll do our next lab next Wednesday, Thursday. So, and like I said, that we have some strange weeks. This week's been a strange week, and a couple of weeks from now is strange as well. But anyways, we're going to get into chapter 4. So here we got some jokes. What did the lawyer name his daughter? What did the lawyer name his daughter? Sue. There you go. What did the mountain climber name his son? What did the mountain climber name his son? Cliff. And what do lawyers wear to court? Lawsuits. Lawsuits. Okay, so here we go into chapter 4. And again, a lot of review. Molarities, dilution, stoichiometry, titration, and we're going to get into some new stuff, some balancing, oxidation, reduction reactions. So this chapter start to get into some new stuff. So here we go. Here are the problems for chapter 4. And again, I really, like I've been saying, I really encourage you guys to be doing the problems that I'm giving you in the book. And now we're starting the 4th chapter. So you've got the problems that I've been giving you, the labs, the reviews, or the quizzes. I've given you a couple of review packets, the ones we do in class. And I think it's really, again, starting to be kind of like a college student, is that, the problems we do in class, I think it would be good to redo those the night after we have had class. And then if you come across a problem in the book that you don't know how to do, then go back and then see how to work it in the answer guide, and then go back and gain understanding, and then in the next day or two go back and try it again. So okay, so there are the problems. Chapter 4. Chapter 4. Types of chemical reactions and solution stoichiometry. So this is about water. And you remember when you guys did the Tinker Toy Lab, if you remember, just like this picture shows, water is a bent shape or a V-shaped, and it's polar. So remember when we diagrammed water, so just real fast here. Diagrammed water in first year chem, and this is again stuff that you guys I'm sure remember, but water had a shape like this, and because the electronegativity value of oxygen was 3.5 and hydrogen was 2.1, that meant that in these two bonds that there's a stronger pull on the electrons, pull of the electrons closer, so the dots representing electrons to oxygen. So what we get is this symbol, and remember this means partial. So we have a partial negative and a partial positive, and that's a very important property of water. See, if water had been linear, then we would have a pull like this and a pull like this, but those pulls would cancel out. In this case, it would have been non-polar. But water is not linear. It's not linear. It's not like this. It is bent. And it's bent because in the dot structure for water, the reason it's bent is because of those non-bonded pairs of electrons there. All that being said, because water is bent, it is polar. And because water is polar, it is very, very soluble. And so it can dissolve ionic compounds. And I'm going to do a demo on Monday, Tuesday, a demo we did in first year chem, but the principle is like dissolves like. And so something that is polar or ionic can dissolve something else that is polar or ionic. So all that being reviewed. So properties of water, it's bent or V-shaped, and it is a polar molecule. And you'll see that delta, the delta up there, this Greek letter delta right here, which is also in that diagram you'll see in our class, and it's always good to represent that. Okay, ionic solids. Ionic solids many are soluble in water. And remember an ionic solid, when we were talking about just kind of reviewing dots a little bit, and we're going to review dots way more later in our class. But we said if we had a non-ionic compound, a molecular compound, we would say like water or methane or ammonia, that is a molecule that has boundaries around it. Well, an ionic solid is not like that. It's this huge lattice. And technically, it wouldn't be right to say it's a molecule, even though we all do. But it's a formula unit is the way to say it. But ionic solids, many are soluble in water. Hydrated ion or hydration, when a cation or anion are completely surrounded by water molecules. And so the dissociation there of NaCl is written down, where you just take the solid and it breaks apart. And these illustrate what happens. And I'm going to stop this for a second and just write a couple things on the board. Nothing that is too profound here, but when you take, so if we've got water which has these poles on it, and if we've got something like an ionic, like salt, something with an alternating positive and negative charge like this, and because water has these poles, so around this positive, the negative water, like the lights, opposites attract and likes repel. And so there's an attraction here. And so what happens is that it pulls that apart, dissociation. And not some ionic solids, we'll look here in a second, they don't dissolve in water. And that's because the force within the crystal is stronger. It's so strong that that won't happen. Most ionic solids, they will dissolve in water. And so to write out dissociation, like we just had our first snowstorm of the year, yes, right after Labor Day. But what they put on streets when it gets really cold and snowy is magnesium chloride. Well, this is how you would write the dissociation of mag chloride. So here's a dissociation equation. Again, a vocabulary from chemistry is all that happens is the ionic solid breaks apart. So we get magnesium as an ion, and the two, you go, wait, chlorine, now remember from first year chem, is diatomic. Well, that is when it is a neutral molecule, but as an ion, it's not. So the two goes to the front. And what we said in first year chem, when we were writing dissociation equations, it's still the same here. When the subscript is part of a polyatomic ion, when you dissociate it, then that subscript would remain if it's part of a polyatomic ion. But if it is not part of a polyatomic ion like this two, then it would go to the front and become a coefficient. Okay, so dissociation equations. Okay, we're going to review in this chapter what we did with writing out molecular equations, complete ionic equations, and net ionic equations. And because of this, and again, I'll do a little demo. I'm going to get out my electrical apparatus on Monday, Tuesday, but we'll talk about electrical conductivity. And when you dissolve an ionic solid in water, it will conduct electricity because of the ions that are free to move around. Okay, next slide. So as I was just talking about, the solubility of ionic compounds in water depends on the strength of the bond between the cations and the anions, and the bonds between the ions and the water. So ionic solids, so salts that are not soluble, and again, there's not a lot of them, salts that are not soluble, their bond between the cation and the anion is stronger than the attraction between the water and the ions. So AgCl is not very soluble in water. Sodium chloride is soluble in water. So the question, which ionic solid has stronger bonds? And the answer to that would be the AgCl. So if an ionic solid does not dissolve in water, which again is pretty rare, but if an ionic solid does not dissolve in water, then its bonds within its molecule is so strong. So the answer to that is AgCl, because it doesn't dissolve. Okay, and then non-ionic compounds. So we're talking about when we have two nonmetals, they're soluble in water if they are polar. A really good example of that is sugar. Sugar is made up of C, H, and O, so all nonmetals. And but it does dissolve in water. And the reason for that is because sugar is polar. And so if there is some polarity, so again, like dissolves like. So even though sugar is not ionic, but it is polar, so it would have a dipole, and a dipole or a hydrogen bond, and so that makes, again, like dissolves like. Grease is nonpolar, and it doesn't dissolve in water. So I'm going to do a demo that I did in first year chem just to review this, and that is I'm going to take acetone fingernail polish remover, and I'm going to put it in a styrofoam cup. Well, both are nonpolar, both are London forces, and so the acetone will actually dissolve the styrofoam in the cup. So like dissolves like, and then if you have an ionic solid that doesn't dissolve, it is because it has such a strong inner force between the ions, it doesn't dissolve at all. Okay, really important. So this table, it says here, you will need to be memorized. Good news, this you do not need to do. Okay, you do not have to remember this list. Now remember, on the back of your periodic tables, I have, grabbing one here, I have put a table of rules. And as long in our class, I will always let you guys use this. So I'll always let you guys use this. But really good news is when the AP redesigned the course, which was now over 5 years ago, instead of making their students memorize that list that I just had up there, they said this is what you got to know. And this is way more manageable. So instead of having to remember all those rules, which if you had an older sibling that had AP chemistry, they had to memorize that. What AP says now, these ions, if you have a sodium, potassium, ammonium, or nitrate, so if you've got one of those four ions, it's going to be soluble, which means it's AQ. Okay, so that's what AP expects you to memorize now. So to me, I always remember this: sodium and potassium, they're alkali metals, so they're right next to each other on the periodic table. Ammonium is the only positive polyatomic ion, and then nitrate. So again, state that again. So if you have one of these four ions in the salt, it's going to be soluble. And that's all that AP will expect you to know. Now in our class, I'm always going to have that table, and you'll have your periodic tables available, so you can always refer back to that. So that's good news. Again, if you had an older sibling many years ago that was in AP Chem, they had to memorize that chart. So good for them, and you guys don't have to worry about that. Okay, aqueous solutions. Okay, and this is something, again, that's going to come up again throughout our class from time to time. An electrolyte solution, a solution that is conductive to electricity because of the presence of dissociated ions in the solution. I always remember an electrolyte, and this is another, I'm going to do a couple demos on Monday, Tuesday. Nothing's going to explode, unfortunately, but an electrolyte turns the light bulb on. It'll turn the light bulb on. So the light bulb, meaning it's carrying electricity. And a strong electrolyte is something that's going to turn the light bulb on, contains a lot of ions. And there's three categories: soluble salts, so that means salts with one of those four ions, probably can't see that now, but sodium, potassium, ammonium nitrate, or strong acids. And there's a list of the 6 strong acids. And for right now, you don't have to memorize that list, but depending on how far we get, and this is, I think it's a chapter 14 topic, and this we'll probably get to, hopefully, but that is a list of the 4 or the 6 strong acids. And again, you could commit them to memory now, definitely will in the springtime. And then the strong bases. So those are the alkali metal hydroxides. So that means, so I'm just going to show you kind of how, of course, I've done this for a long time. But for the acids, if you look on the periodic table, you've got 3 of the 6 strong acids. 3 of the 6 ones come with H. Of course, being an acid, it's got H. So HCl, HBr, HI. So those 3 right there, HCl, HBr, HI. And then there's nitric acid, which we used in some labs, HNO3, sulfuric acid, H2SO4. And then the one that's kind of one that is not familiar is perchloric acid, which is actually the strongest acid there is, which is HClO4. So again, the way I remember the strong acids, again, the halogens, HCl, HBr, HI, not HF. And we'll probably talk about HF. It's kind of an unusual, very strong, weak acid. And then nitric acid, sulfuric acid, and then perchloric acid. For the bases, it's the alkali metals. So this column right here, hydroxides. So LiOH, NaOH, KOH, RbOH, CSOH, and then francium will never come up, as well as calcium, strontium, and barium hydroxide. So CaOH2, SrOH2, BaOH2. So the alkali metal hydroxides, as well as calcium, strontium, and barium hydroxide. Those are the strong bases. So what is a strong electrolyte? Something that conducts electricity well are these categories. So they're a soluble salt. So they're a salt with Na, K, NH4, or NO3. Those are going to dissolve. They're going to produce a bunch of ions. Strong acids, which I was just talking about, and strong bases. Okay, a weak electrolyte. So this is going to, by the name, a weak electrolyte is it's going to produce a few ions. And but not a whole bunch of ions. And so I'm going to show you on Monday, Tuesday, is a weak acid, a strong base, a soluble salt. The light bulb will get really bright because there's 2 electrodes and there's many ions to connect the electrodes. When it's a weak acid, weak base, then there are some ions, so the light bulb will turn on just a little bit. So weak acid dissociates very little into its ions, and a weak base, the same thing. So you go, well, what are the weak acids? What are the weak bases? Well, they're all the other ones. So I just told you the 6 strong acids: HCl, HBr, HI, HNO3, H2SO4, HClO4. All the other acids are weak acids, so hundreds and hundreds of those. And the strong bases were the alkali metal hydroxides, as well as calcium hydroxide, strontium hydroxide, and barium hydroxide. All the other bases are weak bases. So these are going to be weak electrolytes, which means they're going to conduct electricity, but they're going to conduct electricity not very well. Okay, and here's just a good diagram showing what's going on here. So the first one, the one on the left, is acetic acid. And again, it's all the other acids other than those 6. And acetic acid, the HC2H3O2, is the most common represented weak acid that there is. But there's the reaction. And note what it shows. It shows the double arrow. Where in a strong acid, strong base, you should just have one arrow going from the left to the right. On the right side, we've got ammonia plus H2O, and ammonia is the most commonly used represented weak base. And you can see what happens there. Again, a double arrow. And if you look at the illustration, you can see again, there's not very many ions in the illustration. So again, just a point that you guys are probably good with, but just what we're saying here. So if we've got the way that these are represented, so if we've got a strong acid, say HNO3, what happens here is if you put it with water, and one thing I'll talk about as we get later on in the class in the spring, we really go into depth on acids and bases, is you really don't have to write water in here, but you can, and it really doesn't matter. But what happens is we have aqueous, we have liquid, we have aqueous, and we have aqueous. But the arrow is just going to the right. It's going to the right. This is a strong acid. Okay, well, a strong or a weak acid then, like I said, HF, but here I would want to indicate a double arrow. Strong acid would just be an arrow going to the right. I'd still get off H3O, and I get off F negative, and these again would be aqueous. But what happens here when it's a weak acid is it actually goes back to the left more than it goes right, so there's just not very many ions, is what happens there. And the same exact concept with the base. So when you have a strong base, it's got to go completely to the right, so you just have an arrow this way. And one thing we'll talk about with bases, with acids, like you could have written out the equation on the AP test like this, or the way I just had it. It didn't matter if you wrote water or not. HF, it didn't matter if you wrote in water, and both of these, for anybody in chemistry, I think would say that those are acceptable ways to write that. Well, for a base, when the base has OH, like let's say KOH, that's a strong base. You cannot write it with water. You cannot write it with water. It would just be like that. But when you have a weak base like ammonia, you got to write it with water. Okay, and then there's the double arrow because there has to be in the definition. So here's a strong base, and here's a weak base. So I guess the point I'm trying to make here is that when it's an acid, if it's a strong acid, two points. The arrow goes just to the right. If it's a weak acid, it's a double arrow like this. If it's an acid, you can write it on the left on the reactant side with water or without. Both would be acceptable. For base, if it's a strong base and the ones that have OH, which are the strong bases, you can't write water in there. You just have to write it like this and it dissociates. If it's a weak base, you have to write it with water because there has to be a source of hydrogens in there. Okay, almost done here. You just go on to the next slide. Okay, so we've been talking about. Okay, going back here. We talked about strong electrolytes. So these are things that completely dissolve. They conduct electricity very, very well. Second category were weak electrolytes. These conduct electricity a little bit, but not very strong. And then the next category, and this is where I'll stop, are non-electrolytes. Non-electrolytes do not produce any ions, so they don't conduct electricity at all. So non-electrolyte, they dissolve, but they don't produce any ions, usually molecular compounds with only non-metal elements. And so there's examples. Grease is in that category of how that works. So we've got strong electrolytes, weak electrolytes, and non-electrolytes. Non-electrolytes, molecular compounds, two non-metals combined that are not polar, and they do not dissolve in water, and then they don't dissolve in water at all. Remember, like dissolves like. So something that has ionic or polar hydrogen bonded are going to dissolve each other. So if I ask you, okay, would gasoline, which is nonpolar London, dissolve salt? The answer is it would not. So, okay, that's a good place to stop. Guys, thanks for listening, and keep up your AP chemistry and stay on top of it. Talk to you later. Bye.